Hello everyone, myself Dr. Gautam Haldar, Assistant Professor in Mathematics, Malda College, Malda. Today, now we are going to study the theory of set. Okay. The theory of set was developed by G. Cantors, German mathematicians, in the last part of 19th century. And according to him, the definition of set is as follows. A set is a well-defined collection of distinct objects. A set, according to him, the definition of set is a well-defined collection of distinct objects. Okay. Now the set usually is denoted by the capital letters like say A, B, X, Y, etc. And the objects or the elements of a particular set is denoted by small letters like A, B, C, X, Y, etc. Now a set may be of two types. One is a finite set, another is infinite set. Finite set means a set containing only a finite number of elements is called a finite set, and a set containing an infinite number of elements is called infinite set. And naturally, sets can be denoted by the two symbols. One is, if we know all the elements of a particular set, then we can enlist all the elements of the set, and it is denoted by this. Suppose A be a set and the elements of A are all known, say 1, 2, 3, 4, like this up to 50 say. So this is the one way of describing a set. And another this is number one. Number two, if all the elements of a particular set is not known or infinite or uncountable, then that set can be represented by a common character of all the elements. Suppose A be a set and the elements of the set A is like this. Say A X such that X satisfies some certain condition. Suppose X such that X is an even integer. So this is one way of describing the set, and this is another way of describing a set. Okay. So this is finite set because the elements of that set is finite, and this is an infinite set because the number of even integers is infinite. Okay, now let us come to the definition of a null set or empty set. What is called null set or empty set? A set which have no elements is called an empty set or null set or a void set, and it is denoted by the symbol phi. Okay, now let us come to another definition called subset. suppose A be a set. A set B is said to be a subset of A if every element of B is an element of A, and we denote it by the symbol, say B is a subset of A. Okay, now suppose A be a set, this is a set, and X an element, then either this element lies wholly in A, and we denote it by this symbol. This is belongs to, we call it belongs to. Another condition may happen, which is A does not belong to A, and we write it as X does not belong to A, and we call it as does not belong to. Okay, now using this notation we can say that B is a subset of A means X belongs to B implies X belongs to A. One thing we can also say that once if B is a subset of A, then we can say that A is a superset of B, and geometrically it can be thought of as this is my A, bigger set is A, and this is my set B. So this shows that B is a subset of A, or in other sense A is a superset of B, and the notation of superset is this. This is notation is superset, and this notation stands for subset. This notation stands for subset. Okay. Now we have already defined the null set. Null set is nothing but a set which contains no element is called a null set. So by convention, null set is a subset of every set. By convention, null set is a subset of, say, every set. For every set X. Okay, this is by convention, because if this does not happen, that means phi is not a subset of X. This happens only when if we can get some element, say X. This does not happen only when if we can get some X belongs to phi which does not belong to X. But this is not possible because phi has no element. So by convention we can take null set is a subset of every set. Okay. Now let us come to the equality of two sets. Equality of two sets. Suppose A and B be two sets. We say that A is equal to B if and only if this notation stands for if and only if. This means if and only if. If and only if A is a subset of B and B is a subset of B. Then we can say that A is exactly equal to the set B. Okay. Now let us come to another concept called power set. Let's come to another concept called power set. Suppose X be any set, then the power set of X denoted by P of X is the collection of all subsets of X. The collection of all subsets of X is called power set of X. Means P of X is equal to A such that A is a subset of X. This is the symbolical notation of a power set of a set X. Sorry. Okay. Now let us try to understand this by taking some example. Suppose our X is equal to say 1, 2, 3. Then how many subsets we can get from this set? One is 5, as we have already said that the null set phi is a subset of every set. So this should be a subset of X. Another is singleton 1, another is singleton 2, another is singleton 3, then 1, 2, then 1, 3, then 2, 3, then 1, 2, 3. So all these subsets, we take the collection of all these subsets and we call it the power set of X. We call it the power set of X. Okay. One thing we should notice from the above discussion, that if the number of elements of X denoted by this stands for the number of elements of X. So here is number of elements is 3. Right? 1, 2 and 3. So number of elements of X is 3. Therefore, number of elements of Px, is 1, 2, 3, 4, 5, 6, 7, 8, which is nothing but 2 to the power 3. Similarly, if we take a number of elements, if we take a set which contains the number of elements 4, then the corresponding power set will contain the number of elements is 2 to the power 4. And likewise, if the number of elements of a set, particular set say X is n, then the number of elements of the power set of X will be 2 to the power n. Okay, what happens if we take the set X as null set? Suppose X is equal to 5. Then the power set of phi will be singleton set phi. So power set of phi will be a singleton set, and that is nothing but this. Okay. Now, once we understand the definition of set, then we try to understand what are the operations on a particular set. So, in fact, there are mainly 3 types of operations. So before going to discuss the algebraic operations on a set, let us try to understand what is called universal set. Universal set. Okay. Universal set is usually denoted by the capital letter U, and universal set is not a fixed set or a unique set. It depends on a particular problem. Suppose we take a problem, say suppose x is equal to say 1, 2 and y is equal to say 3, 4. Okay, then for that particular problem, if we take say u is equal to say 1, 2, 3, 4. So universal set, definition of universal set is nothing but a set which contains all the set regarding to the particular problem. That set is called a universal set. Okay, so universal set, definition of universal set is a set which contains all the set for a particular problem is called universal set. Okay, now let us come to the algebraic operation on set. Algebraic operation on a set. Algebraic operation on a set. Okay. One algebraic operation on set is called union. A notation of union is this. Suppose A and B be two sets. Then the union of A and B denoted by A union B is defined in this way. X belongs to or X such that X belongs to A or X belongs to B. Right? That means the union of two sets A and B contains all those elements which are from which may come from A or which may come from B or which may come from the both sets A and B. So this is the definition of a union of two sets of the union of a two sets. One thing we should notice that here we have used the word or. Let us try to understand what is the meaning of that word or. Let us take a statement. Suppose it is either it is raining or it is not raining. Here also we have used the word or. But what is the difference between these two or? The difference is that here there is two statements. One is it is raining and another is it is not raining. So once we use this or in between these two sentences, that means either this statement will happen or this statement will be happening. Okay, but at both the statement will not be true simultaneously in English literatures. Okay, that means either it is raining or it is not raining, but both things cannot happen simultaneously. But here both things may also happen. That means either X belongs to A or X belongs to B, or X comes from the both the sets. So this is the difference between this or and this or, and this or is called inclusive or. But this or is called exclusive or. Okay, so this is the difference between these two or. Now come to another operation called intersection. Notation of intersection is this, and the definition of intersection of two sets A and B is this: A intersection B is equal to X such that x belongs to A and x belongs to B. X belongs to A and x belongs to B. Okay. So diagrammatically, suppose this is my A, this is my B. So A union B will be the whole set. This is my A union B. But A intersection B will be the common portion of these two sets, and this portion is the A intersection B. So it is clear from this picture that A subset of A union B, B subset of A union B, again A intersection B is a subset of A intersection B is a subset of B. So these four things is clear from this picture. Okay. Now let us come to another operation called complementation. Complementation. Suppose U be the universal set. Suppose U be the universal set, okay, and A be a subset of U. A be a subset of U. Then the complementation of A denoted by A prime, or it is also be denoted by a complement, and is defined as X belongs to U such that X does not belong to A. So it is something like this. Suppose this is my universal set U, this is my set A, then A dash will be the set of all elements which does not belong to A. That means this portion will be our A complement. This portion will be our A complement. Okay. Now let us come to another operation called difference of two sets. Difference of two sets. Difference of two sets. Suppose A and B be two sets. Suppose A and B be two sets. Okay. Then A difference B is defined as X belongs to U such that X belongs to A, but X does not belong to B. X belongs to A, but X does not belong to A. It can be seen in this way. Suppose this is my universal set U, this is my set A, this is my set B. So A minus B is all those elements of A which does not belong to B. That means this portion is a common portion of A and B. So the portion, these elements of this portion also lie in that portion. So this must be excluded here. So this portion is my A minus B. This portion is my A minus B. Similarly, B minus A will be the X belongs to U such that X belongs to B, but X does not belong to A. So B minus A will be that this set will be my this set. This portion is my B minus A. Okay. Now from this picture we can observe some simple results. As we've already said that this portion is my A intersection B. So if we add A intersection B to A minus B, then we can get the whole set A. So A will be A minus B union A intersection B. Similarly, B can be obtained in this way: B minus A union A intersection B. Okay. Now let us come to another definition called disjoints. What is called disjoints? A and B, two sets, are said to be disjoint if they have no element in common. That means the intersection of A and B is equal to phi. Then these two sets are called disjoints. So if this happens, then we say that A and B are disjoint set. A and B are disjoint set. So from here we can see that A minus B intersection B minus A is equal to phi. That means A minus B and B minus A are disjoint sets. Also, A minus B and A intersection B are two disjoint sets. Also, this is A minus B intersection A intersection B is equal to phi. Number 3, B minus A intersection A intersection B is equal to phi. So we have understood the disjoint sets. And also we saw some examples of disjoint sets. Okay. Now as we have already defined, the complement of a set A is nothing but X belongs to U such that X does not belongs to A. So from there we can say that suppose this is my universal set U, this is my set A, so A dash will be this. So we can see from this picture there A dash is nothing but U minus A. Okay. There is another operation called delta operation or symmetric difference. Symmetric difference of two sets. Okay, what is this? A delta B is equal to A minus B union B minus A. So this is the definition of symmetric difference, delta. Okay. Okay. Now there are some simple properties that we need to understand, and the properties are as follows. Some simple properties. Some simple properties. Suppose U be the universal set. X, Y, Z be any three sets in U. The number one property is X union U. Okay, this universal set is equal to X. Sorry, this is equal to U. X intersection U is equal to X. Number two, X union phi is equal to X. X intersection phi is equal to phi. Number three, x union y is equal to y union x. This law is called commutative law. So union of the operation union of two sets is commutative. Number 4, associativity means x union y union set is equal to x union y union set. This is called associative law. Number 5, x union y intersection z is equal to x intersection z union y intersection z. X intersection y union z is equal to x union z intersection y union z. These are all simple properties that you can check easily. These two properties are called distributive law. These two properties are called distributive law. Okay. Next, come to another definition called Cartesian product of two sets. Cartesian product of two sets. Suppose A and B be two non-empty sets. Suppose A and B be two non-empty sets. Then the Cartesian product of A and B is defined in the following. Cartesian product of two sets A and B denoted by x cross B is another set, and the elements of that set will be of the form x comma y such that first component x comes from the first set A and the second component y comes from the set B. So Cartesian product of two sets is the set of all elements, so set of all ordered pairs of elements x comma y, for which the first component x will come from the first set A and the second component y will come from the set B. So naturally A cross B is not equal to B cross A in general. That we can easily see by taking some examples. Okay. Now let us come some simple results on complementation. Okay, some results on complementation. Suppose U be the universal set. A and B be any two sets of U. Okay. Then the properties one is A dash dash is equal to A. Okay, we should write it here later, but okay, it's not a problem. Suppose the complementation of U is equal to phi. The complementation of phi is equal to the universal set itself. Okay, number 3. A union A complement is equal to the universal set. A intersection A dash is equal to phi. Number 5. Okay, we have already written here. Okay, the next is A union B complement is equal to A complement intersection B complement. A intersection B complement A is equal to this. This two law is called DeMorgan's law. Okay, now we prove this portion only of DeMorgan's law. Proof. Okay. To prove this, that means left hand side is a set A union B complement, right hand side is also a set A dash intersection B dash. So to prove these two sets are equal, we need to prove the following: A union B dash subset of A dash intersection B dash and A dash intersection B dash subset of A union B dash. Okay. Now let us first prove this one. So suppose X belongs to A union B dash. So this implies X belongs to U but does not belong to A union B. So this implies X belongs to U but X does not belong to A and X does not belong to A. Here we have put AND because since X does not belong to A union B, that means X does not belong to any one of these two sets. Okay, that's why I have put here AND. So this implies X belongs to U but X does not belong to A and X belongs to U but X does not belong to B. So this implies this one is X belongs to A complement and X from this X belongs to B complement, and this implies X belongs to A dash intersection B dash. So from this A union B dash subset of A dash intersection B dash. Okay, in a similar manner we can show that this in a similar manner, but means we can go back from downward to upward and we get this one. Okay, so similarly A dash intersection B dash. So from 1 and 2 dash is equal to intersection dash. So this is the one part of the DeMorgan's law. Okay. Okay. Now I would like to discuss one more important things, which is as follows. Okay. Just before we have said that union, intersection, and Cartesian product of two sets. So these three operations, these two operations and this notion have been defined on two sets. Now this notion can be generalized to any number of or any arbitrary number of sets. So suppose A1, A2 up to AN, these are all finite number of sets. Then union of all those sets denoted by this is defined as X, such that X belongs to AI for some I. So for some I, say comma 1 less than equal to I less than equal to n. Intersection of this set denoted by this is such that X belongs to AI for all I 1 less than equal to I less than equal to n. Okay. And the Cartesian product of these sets, this n set number of sets, is defined as A1 cross A2 cross up to cross AN is equal to X1, X2, Xn such that Xi belongs to AI 1 less than equal to I less than equal to n. Okay, so with this I stop here. Thank you very much.